Alright, ladies and gentlemen, we are going to be taking a look at Coulomb's law today. That is going to be one of our new equations that we're going to develop. This is all coming off the electrostatics lab. If you're in class today, some of this will be recap, so you can kind of speed ahead if this all makes sense. There'll be a nice little piece in there that is going to be new, though, that talks more about Coulomb's law, so make sure you hit that. For those who are missing, I'd say stick around for the whole entire thing. Should really recap a lot of the things that we talked about today in class. So, taking a look at this, targets for today. I know the relationship between the electrostatic force and R. There is a weird relationship between these two, and that relationship between the electrostatic force and R is different than what we're normally used to. You will see that we will spend a lot of time talking about proportions. This will bring it really to a better understanding and really kind of iron out a lot of the misconceptions with this relationship. Number two, I understand and can use Coulomb's law. Whenever we look at a law, by the way, this is going to be a formula that we get. This formula, always make sure you understand terms in formula. That means what does the F mean, what does the K mean, all that other good stuff. Make sure you know the units for each one of the terms so you're using those properly in problems. And part C, what it represents. Anytime somebody solves for a value in a formula, you got to be able to describe what is that number actually telling you. That's usually where physics students go wrong. And number three, I can solve Coulomb law problems. I'm just going to go over very simple, just things to look for, things to think about, what this is really kind of breaking down into. So, taking a look at number one is going to send us down right on over here, the relationship between the electrostatic force and R. So, first things first, we saw a graph in class that looked like this. What is this graph telling you? Well, as you can see, as R increases, FEL decreases. So that means as I take two charges like this and I move this charge further away, what is happening? The force is getting smaller. So that makes sense. However, we need to take this one step further and we need to actually understand the proportion, or what is FEL actually directly related to. You'll notice that this is not a direct proportion because it's not a straight line. So usually in your methods that we've learned in class, you'd say, I'm going to do 1 over R. And when you do 1 over R, close but no cigar, you'll start to see it is starting to become a straight line, but it still has a slight curve to it. This is why this formula gets kind of tricky, because this extra little curve, which means we need to do one more modification, which means we need to break this down all the way down to 1 over R squared. When we finally do that, we will get a straight line. So, straight lines mean direct proportions. So what I can actually write in this case is FEL is proportional to 1 over R squared. By the way, the fish sign there just means proportional. What does a proportion tell us? It does not tell us an equation. A lot of people think a proportion is equivalent. There's a reason why I don't write an equal sign. It is not directly equivalent. What it can tell you is if you change a value by so much, how much it is going to actually affect the original force. So, for instance, I can look at a situation where I have two charges, and these two charges are separated by a distance, what we're going to call as R naught. I do R naught because it is going to be the initial R value in this case. If I go on over here, I could say maybe this force value is 5 newtons. By the way, this is what we could call the original force value, F naught. So I can say that F naught is proportional to 1 over R naught squared. So that is the proportion that we know. Now, what I could then do is I could say, well, what happens if I take the original value and cut it in half? So R naught divided by 2. And I can ask the question, what is my new F? So in this case, what we need to do is we need to go back to the proportion. Well, I can go back into it and I could say F naught is proportional to, well, we have now 1 over, well, our radius in this case, the R value from our original value is now going to be R naught over 2. And we're going to be taking that whole thing and squaring it. So if I calculated this, you will see a value of 1 over R naught squared over 4. And if I rewrite this, we will get 4 over R naught squared. Now you might be looking at this, you're like, what is this telling us, Mr. Z? What are you actually saying in this case? Well, if I had to rewrite this, I can rewrite this as by saying, well, this is 4 times 1 over R naught. Or in other words, this is 4 times, remember, 1 over R naught is the original force value that I had. So in this case, I could say it's 4 times the original force. So when I re-look at this example, I have just discovered that if I cut my original radius in half, I will get 4 times the original force. So if I go back to my original force is 5 newtons. So I take 4 times 5 newtons, and that will give me a total of 20 newtons. So you look at this and you can say, oh, hey, by cutting something in half, I will take that original force value and multiply it by 4. Interesting things that start to occur. You could start to say, well, what if instead of R naught over 2, I do R naught over 3? So you'll notice that this value will get, or this distance will get a little bit smaller, and then you'll notice that, wait a minute, by doing those calculations, you should probably try them out at home right now if you haven't done so already, or do it in your head. Hit pause if you're going to be doing that. And if you do that, you're going to see that it comes out to be 9 times the original force value. So as we make these two protons get closer and closer and closer, we're seeing an exponential increase in the amount of force. I'm sorry, when I say exponential, I mean a power function, a squared 1 over r squared increase in this force value. So this gets, let's go back to this. This gets kind of interesting because now you start saying, where do I actually see protons really close together? And if you've ever drawn this picture before, you might remember, oh hey, that's the nucleus of an atom. And this has some really interesting applications. You can actually calculate the force between 2 protons in an atom, and those forces can get rather large. Especially when you start packing a lot of atoms in there. So this idea of 1 over r squared can get kind of tricky. So going back on over here, I know the relationship between the electrostatic force and r. We just did proportion. Check there, number 1 done.